Okay, so you're here, you're listening in because, AI is everywhere, right? It's changing the world and you want to understand how it all works. I get it. And today we're diving deep into one of the most fundamental technologies that makes those mind-blowing AI models tick. We're talking large language models, LLMs.
Right. And more specifically, we're going to untangle this concept of self-attention.
Hmm.
Now, you've probably heard of GPT or BERT, right? These are the engines behind so much of what we see in AI these days. And guess what? Self-attention is the secret sauce that makes them so powerful.
Yeah, it's the thing that allows these models to really grasp the context of language, the subtle ways that words connect and influence each other. It's like how they can hold a conversation, translate languages, convincingly, or even whip up a poem or a story. So no matter what field you're in, the stuff is getting more and more important to understand.
Absolutely. And to help us navigate this complex topic, we have a fantastic article by Victor Lung. It's called Understanding Self-Attention in Large Language Models, LLMs, Continuous Improvement. And Lung does a great job of breaking down self-attention. He talks about its strengths, the challenges of making it work with really long texts, and the exciting new innovations like sparse attention and ring attention that are really pushing the boundaries of what's possible.
So today we're going to unpack all of that. We want to give you a clear understanding of how self-attention works, what these new developments are all about, and basically just demystify the whole thing. So first things first, what exactly is self-attention?
Well, at its heart, self-attention enables a model to look at all the parts of an input sequence. Imagine all the words in a sentence and figure out how important each word is relative to all the others in that sentence all at the same time.
Right. So it's not just processing words one by one, like reading a shopping list. It's more like reading a sentence and understanding how the meaning flows through it, how words connect and create meaning together.
Exactly. And that's a big shift from older methods that could only process things step by step. This simultaneous approach makes self-attention much more efficient, especially when dealing with massive amounts of data.
Okay, so how does it actually do this simultaneous analysis? I keep hearing about these query key and value things. Can you explain those a bit?
Sure. So um, for every token in the input, and a token could be a word or even part of a word or even a character, the model transforms it into these three vectors, query key and value. They're generated using some learned weight matrices. And think of the query vector as the question that a token asks about all the other tokens in the sequence.
So like each word is saying, hey, everyone, how do you relate to me in this sentence?
Yes. And then the key vector of each token is like its response or its ID card.
Mm.
It shows how relevant that token is to the queries from all the other tokens. And the value vector, well, that holds the actual information, the content of the token, which will be used later.
Okay, so we've got all these questions and answers swirling around inside the sentence. What happens next? How do they figure out which connections matter most?
Well, the next step is calculating those attention scores. This is done using the dot product of the query vector from one token and the key vectors of all the other tokens, including itself. And this dot product gives you a score, a measure of how well those two tokens match or relate in that specific context.
So the higher the score, the more important those two words are to each other in that sentence, right?
Right. But then we've got all these raw scores, so we need to normalize them, make them more manageable.
Yeah.
That's where the softmax function comes in. It turns these scores into probabilities, or attention weights, that all add up to one for each token. These weights tell us how much attention each token should pay to every other token in the sequence.
So now we know how much each word should be focusing on the others. But how does that actually translate into understanding the meaning?
Well, that's where the value vectors come back into play. We take the value vector of each token and multiply it by its corresponding attention weight. And then we sum up all these weighted value vectors. And this creates a new context-aware representation for each token. It's like the model has taken the whole sentence into account and refined its understanding of each word based on its relationships with all the others.
That's a cool way to put it. Each word gets a more nuanced and complete meaning after this whole self-attention process.
Exactly. And the article also mentions this thing called scaled dot product attention, where you scale those initial dot products by the square root of the key vector's dimensionality. And that might sound a little technical, but it's actually really important for keeping those attention scores from getting too big during training, which can mess up the learning process.
Right. Scaled dot product attention keeps everything running smoothly. Okay, so now we know how self-attention works. But why was it such a game changer for LLMs?
Well, there are a few key reasons. First, it's amazing at capturing long-range dependencies. Sometimes in a long sentence or paragraph, the subject might be way at the beginning, and the verb that goes with it might be much later. Older models really struggled with connecting those distant pieces of information. But self-attention can directly attend to those faraway words and understand the relationship.
That's huge, especially when you think about things like understanding the plot of a novel or a complex scientific paper where ideas are spread out across many pages.
Exactly. And then another big advantage is contextual understanding. So many words have multiple meanings right, and the only way to know which meaning is right is to look at the surrounding words. Self-attention helps the model do just that. So, for example, the word bank could mean a financial institution or the edge of a river. Self-attention allows the model to pick the right meaning based on the context of the sentence.
So it uses the surrounding words to figure out what's going on. Makes sense. What other benefits does self-attention offer?
Well, another big one is parallelization. Since self-attention processes all the tokens at the same time, it's much more computationally efficient than those older step-by-step models. And this isn't just faster for training the models. It also means faster response times for us when we're using these AI tools.
So it's not just smarter, it's also speedier. Win-win.
Absolutely. And the last thing I'll mention is that while self-attention started in natural language processing, it's actually proving to be incredibly versatile. Researchers are using it in other fields like computer vision, where it helps models understand the relationships between different parts of an image. And even in recommendation systems where it can figure out your preferences based on your past interactions.
Wow, that really speaks to its power and flexibility. Okay, so self-attention is clearly a big deal, but the article mentions some challenges with scaling it up. What's the main bottleneck there?
Yeah, the biggest hurdle is its computational complexity. Traditional self-attention requires a lot of computation, and it gets worse as the input sequence gets longer. In fact, it has a quadratic relationship with the input length. So if you have a sequence of n tokens, the number of computations grows roughly proportional to n squared.
So if you double the length of the text you give it, the workload doesn't just double, it quadruples. Yikes.
Yeah, exactly. Imagine processing a sequence of 10,000 tokens like a long article or a short story. You need to compute this massive 10,000 by 10,000 attention matrix. That takes a ton of memory and slows things down a lot. It makes it really impractical for working with truly long documents or conversations.
That makes sense. So how are researchers dealing with this scaling problem? That's where sparse attention and ring attention come in, right?
Yep. Sparse attention is one way to tackle this. It's all about reducing the number of attention calculations. Instead of having every single token pay attention to every other token, sparse attention gets strategic. It limits the connections, only focusing on the most important ones.
So it's like saying, hey, not every word needs to be best friends with every other word in the entire text. How does it decide which connections to keep and which ones to drop?
There are a few different approaches. Sometimes you can use fixed sparsity patterns, where the model only pays attention to a small window of neighboring words, or to a specific set of words that are known to be important for long-range context. But sometimes the model actually learns which connections are crucial during training. This is called learned sparsity. It's pretty amazing.
That's wild. The model figures out who it needs to pay attention to.
Yeah, it's pretty cool. There's also block sparsity, where you divide the input into blocks, and the main attention calculations happen within those blocks, which keeps the attention matrix smaller. And there are even more sophisticated methods that use hierarchical structures to capture both local and global relationships efficiently, without needing full attention between every single token.
So by being more selective about which connections to make sparse attention saves a lot of computational effort. What are the main benefits of using this approach?
Well, it requires less memory, so it can handle longer sequences than traditional self-attention. It also has the potential to be optimized for specific tasks. For example, in machine translation, sparse attention might focus more heavily on the core parts of a sentence like the verbs and nouns, and less on the articles and prepositions.
That's a smart way to prioritize. Now, what about ring attention? That sounds like it's taking things to a whole other level. What's the deal with that?
Yeah, ring attention is a game changer for processing really, really long sequences, like near infinite context lengths. It's a newer technique that relies on distributed computing across multiple processing units, often GPUs arranged in a ring structure.
A ring of GPUs. That sounds intense. How does that actually work for processing language?
So you take your super long input sequence and break it into chunks. Each device in the ring is responsible for processing one of these chunks. Now, within its chunk, each device does the regular self-attention calculations and all that. But here's the key. While it's working on its chunk, it's also sending key value information to the next device in the ring and receiving data from the previous device.
So it's like this constant flow of information moving around the ring?
Exactly. This overlapping of communication and computation is what makes it so efficient. And because those attention values are calculated as the data moves around the ring, the model doesn't need to store that entire massive attention matrix all at once. That's what lets it handle those enormous contexts.
So no more memory meltdowns, even with crazy long sequences. That's impressive.
Yeah, it is. And as you add more devices to the ring, you get almost linear scalability, which means you can keep handling longer and longer sequences. It's pretty mind-blowing. We're talking about being able to process an entire book or a super long legal document in one go. That's something traditional self-attention just couldn't dream of doing.
Yeah. So ring attention is the key for when you need AI to understand really vast amounts of information all at once.
Exactly. And the article has this handy table that compares traditional self-attention, sparse attention, and ring attention side by side. It shows you that the key differences in terms of their computational needs, their focus, their scalability, their memory usage, and when you'd want to use each one.
So just to recap, we started with traditional self-attention, which is powerful but struggles with long sequences. Then came sparse attention, which makes things more efficient by being picky about its connections. And now we have ring attention, which can handle almost unlimited context lengths thanks to its clever use of distributed computing.
It's a clear progression, driven by the need to process more and more complex information. And these innovations are essential for the future of LLMs as they try to handle larger and larger data sets across all sorts of applications. I mean, imagine an AI that can summarize entire libraries of books or analyze years of legal documents. That's the kind of potential we're talking about.
And for someone like me who just wants to keep up with all this AI stuff, understanding these underlying mechanisms is so valuable. It helps you see past the hype and grasp what's really going on.
Totally. It gives you a deeper understanding of both the amazing things these technologies can do and the limitations they still have.
So as this technology keeps advancing, it really makes you wonder, how will the ability of AI to process near infinite amounts of information change our world in the coming years? What will it mean for our work, our lives, our understanding of the world? It's a pretty mind-blowing question to ponder.
It is. And if you're curious to learn more, I encourage you to dig into some of the specific applications of sparse attention and ring attention that are out there. There's so much fascinating research happening in this field.
Definitely. Well, thanks for joining me on this deep dive into self-attention. It's always great to explore these complex topics together.
My pleasure.
And for all of you listening out there, keep those brains buzzing, and we'll catch you in the next deep dive.